So in this part of the lecture, I want to describe that another relationship between the electric field and the potential. The relationship in particular is the one that's sort of indicated by the title of this lecture, that the electric field is -1 times the slope of the potential. And I'll just ask you quickly to recall that the slope of a function is the derivative of the function. So what the title is indicating is the electric field is -1 times the derivative of the potential. And this comes from, essentially you just can think of it with the fundamental theorem of calculus. So the fundamental theorem of calculus, one of the ways to write it is to write it this way. If we have two functions, a function f and a function g, right? So f and g over here, and they have a relationship. So if the relationship between the functions f and g is such that f is the derivative of g, then you can be confident that the opposite is true as well, that g is the integral of f. So if f is the derivative of g, then g is the integral of f. And this is the sort of fundamental theorem of calculus. And I'm pulling a little bit of a fast one in the integration, because the truth is this is true up to a constant, right? Yeah, so that's true up to a constant. I have an example from your earlier physics classes that you would learn about when you learned about kinematics. So kinematics is sort of the physics of the relationships between motion and position and acceleration. So the position can vary in time and the velocity can vary in time, right? But we know that the velocity is defined as the time rate of change, or the time derivative of the position function, right? This is the definition of the velocity. And if you have motion, then your location can change. That is, you can have changes in your location. So the opposite sort of way of thinking about the relationship between velocity and position is you say that you accumulate a change in location if you have motion for time, right? And so the change in location, or the displacement, equals the integral of v dt. And that's just the fundamental theorem of calculus. That's the relationship between two functions where one function is the derivative of the other function. So we have this definition that there are changes in the potential because, or there is a difference in the potential between two locations in space because there is electric field between those two locations in space. And if you go through the motions of finishing out this integral between the two locations of space, you'll get your potential difference. So this says that the potential difference is the integral of the electric field, right? But with a minus sign. Remember, in the title I say that the electric field is -1 times the slope of the potential. So that -1 is right here. So we can say that the electric field is somehow related to derivatives or the slope of v. So it's a little bit complicated because the potential v is actually three-dimensional in general, right? So locations in space are represented by three sort of coordinate values. And the electric field is a vector, which is also, though, a function of x, y, and z. So when you ask what the slope is, right, when we talk about slope for velocity, the slope is with respect to time. It's not even got to do with space. But up here, if I have functions of space, like the sort of the f and the g example, the derivative, when I ask for the slope, I only am asking about the slope in one direction because I only have one direction in the space up here. So over here, the slope actually, I can ask about the slope in different directions. I can ask what's the slope in the x, the slope in the y, and the slope in the z. And that, in fact, actually, that's how the electric field is related to the derivative of the potential. The way we say it is the x component of the electric field. Actually, let me do this. Remembering that the electric field is the x component times I hat plus the y component times j hat plus the z component times k hat, where each of these components is actually a function of all three space coordinates, right? So the x component, even though it's the x direction part of it, that x direction part can have variation over the three dimensions of space. Likewise, for the y component, it's a function of all three parts of the coordinate, and the z, also the same, right? This is in general true, right? So the way that the potential and the electric field are related in terms of a slope rather than an integral, that they're related through an integral this way, but they're related through a slope this way. We say that the x component of the electric field, which is a function of x, y, and z, is equal to the negative of the derivative in the x direction of, the potential, which is a function of x, y, and z. This is a partial derivative. So this is an important difference compared to what we understand as a normal derivative. I'm going to just mention that it's a partial derivative and ask you to do your own research on why it's important that I say that it's a partial. But I'll just move on. So the y component is a similar thing, but it's the derivative of the potential in the y direction, and the z likewise. So that super important negative sign, right? The negative sign is very important. It's the derivative with respect to z of the same function v, right? Which is a function in general of x, y, and z. So, actually, let me write this on another page. So, if v does not vary in a direction, then the electric field in that direction is zero, right? For example, what if the variation, right, the derivative of x, of the potential with respect to x, what if this is zero? This means that the voltage doesn't change when I look at two nearby x positions, right? So if I imagine making a small change in location in the x, I find that there is no change in the potential between those two nearby places, right? If I find there's no change, then that means there must not have been electric field in that direction. That doesn't mean that the electric field in the other directions are zero necessarily. It just means that the electric field in that direction is zero, right? Yeah, and this is related to equipotential surfaces and volumes. So here is an example. And it's the point charge. So real quick, let's imagine a point charge. I'm going to place it at the origin. There it is right here. And I'm going to talk about coordinates x, y, z, where I can ask what's the electric field over here, right? So I already know the answer. The electric field is equal to K times Q divided by the distance out to the place squared, right? So R is this distance here. But then I have to multiply by a little r hat vector, right? The unit vector that tells me the direction of the electric field. So a couple things. So R is x squared plus y squared plus z squared. These are little 2's, but remember that it's the square root of the sum of the squares, right? Pythagorean theorem, where r is the hypotenuse. So that's what r is. So I know what how to write down r squared, and r hat is the r vector divided by the length of r. So here's the length of r. That's the thing above, and the r vector is equal to x I hat plus y j hat plus z k hat, right? So the r vector is the vector that takes me from the charge q out to the place P, whose coordinate is x, y, z, where I want to know the value of the electric field. So the r vector points out to there. So in this case, the r hat vector is the vector that points right there. That's the little r hat vector, right? It's a little unit vector that points the correct direction for the electric field. If Q was negative, then that negative sign would be in this equation, and that negative sign could be interpreted as flipping the direction, right? So the electric field of negative charges, those field lines go in towards the charge, and you'd have little unit vectors that point inwards towards the charge instead. But let's think as an example, let's think of Q as a little positive charge. But anyways, I want to finish out my example. The example is, so if I have all this stuff, I bet you can see that the x component is just, right, k, q over x squared plus y squared plus z squared, all squared, right? That's the electric field, multiplied by r hat. R hat is an x component, a y component, and a z component, but I only want the x component because I want to know what the x component of the electric field is. So that's x over, and don't forget that the r hat vector divides by the length of r. So that's x squared plus y squared plus z squared on the bottom with a factor of 1/2, right? So this is the electric field in the x direction. And I want us to remember this because I'm going to derive it a different way. The way that I want to derive it for you is to use this other way. So I'm going to start from the potential. I'm going to take the derivative, and then I'm going to apply a minus sign. And what I want to do is, if I do the steps of starting with the potential, take the derivative in the x direction, then multiply by -1, I want to see what I get if I do that. So let's do that now. So the potential of a point charge is written this way, kq over r, and r we've actually written it down already. It's just the Pythagorean hypotenuse. So it's x squared plus y squared plus z squared to the half power. And so what I need to do is I want to calculate what is the negative of the derivative in the x direction of this potential function, which is a function of x, y, and z. So it's negative d by dx of all this stuff up here. It's kq over x squared plus y squared plus z squared square root. All right? So let's go through and do this. So the k and the q, they are constants. They have no variation with respect to changing the x value. So they come out. So I've got minus kq out front. And now I have to take the derivative. So the derivative is complicated. I'm going to just say out loud what I'm doing. And on a separate piece of paper of your own, I challenge you to do it for yourself. But what happens is, so you've got this x squared plus y squared plus z squared with a square root on the bottom. So I'm imagining this being x squared, plus y squared plus z squared with a negative 1/2 on the top, right? That's just mathematically true, and it's sort of easy to imagine taking the derivative this way. So then I've got minus kq. So if I take the derivative, I get minus 1/2 times the stuff inside the parentheses raised to the negative 3/2. So I'll just write out what I get. So I get a factor of minus 1/2. I get this stuff raised to the negative 3/2 instead. And then I have to multiply by the derivative with respect to x of the inside of the parentheses, right? This is the chain rule. So that gives a 2x, right? So what you can see happening is this 2 and this 1/2 are going to cancel each other, or you can put them together to make a factor of 1. This minus sign and that minus sign hit each other and make another factor of 1. And so if I write down what I've got now, I've got the minus signs cancel and the half and the 2 cancel, and I'm left over with kq over x squared plus y squared plus z squared. This is all raised to the 3/2 power. Man. And then I've got this factor of x. But I'm going to go a step further, right? Remember that 3 over 2 is equal to 1 plus a half, right? So this is kq over x squared plus y squared plus z squared raised to the first power. That's the 1. And then I'm going to take the x that's a little stray and divide it by the rest. Right? So what does this look like? This thing right here is actually r squared, right? X squared plus y squared plus z squared to the exponent 1 is the hypotenuse squared. So there's kq. I've got x over r. So if I go up and compare, do you see this? This is that first power, and this is the square root part, which is just r. So here's r squared and r. Here's x over r. And this is kq over r squared. And they multiply each other, and this is e sub x. Right, so I've got it from 2 directions. So all this is to say is the the way that you see the relationship between the electric field and the potential, you've got now two ways to see it. If you know the electric field, you can calculate the potential just by integrating it. But in this case, I've showed you, if you know the potential already, you can calculate the electric field. But you have to be really, really careful. In order to use for example, this expression, you must know at least how v varies with x. If you don't know that, then you might be misled because you'll take this derivative of some function that doesn't show you how x varies or how the potential varies if x changes. That derivative, you will naively get the result 0, and you'll say, oh, the electric field must be 0 in the x direction. But that'll be a mistake because you started from a function that didn't tell you about how x varied. So I'll just stop there. I think you can tell what I'm trying to say.